This is the 23rd video supplement for CIS 351, Grand Valley State University's course on Computer Organization and Assembly Language. This video discusses latches. Up till now, our focus has been on combinatorial circuits. The key feature of combinatorial circuits is that the outputs depend solely on the current value of the inputs. In other words, the output is a combination of the input. This means that for any specific input, the circuit will always produce the same output. For example, when you put 13 into the is prime circuit, the answer is always yes. We're now going to begin discussing sequential circuits. Sequential circuits can store data, and therefore the output doesn't depend solely on the current input. Instead, the output depends on the sequence of inputs. Each input in the sequence can modify the stored data, which in turn affects the output. For example, we could build a circuit that takes as input a sequence of letters and counts the number of vowels. And so each time we give it the letter E as input, we would get a different output. 1 the first time, 2 the second time, 3 the third time, and so on. Every time the circuit sees an E as input, it updates its data, which in turn affects the output. And of course, what this means is that identical inputs need not produce identical output. We can put E into the circuit many times and get a different output each time we do that. The first thing we need to build a sequential circuit is a means of storing data. One type of circuit that can store data is called a latch. Remember back in video 7 when I said that circuits shouldn't have loops, and then used a bunch of weasel words like usually? Well, we're about to see the main exception to that rule. We're going to use a feedback loop to store data. So to see how a loop can store data, we're first going to start with this circuit. It isn't complete and we really can't use it in a practical sense, but it will help illustrate the key idea of how a loop stores data. Suppose I wave my magic wand and make the right-hand wire a logical 1. The NOT gate at the bottom will then cause the left-hand wire to have a logical 0. The top NOT gate will then reinforce the 1 on the right wire, and so on. So this feedback loop is in a steady state and is effectively storing the value 1 in that right-hand wire. Once I put a 1 on that wire, it'll just stay there. Now, if I were to wave the wand again and make the right-hand wire a 0, then the feedback loop will also be in a steady state, but will store 0 in the right-hand wire. Now let me make one small cosmetic change. I'm going to put a twist in this loop so that both gates face to the right. It doesn't change the behavior of the circuit, just how it looks. Now, as I said, the circuit as is isn't useful because we have no way to set it, no way to intentionally put it in the state we want it in. So we need to figure out how to incorporate some external input. To do this, we'll change the NOT gates to 2 input gates. The second pin for each gate will be our external inputs. So pause the video and try some different 2 input gates and see which ones lead to useful circuits. One possible solution is to use NOR gates. By convention, we label the 2 inputs R and S and label the output Q. It's also common to label the output of the other NOR gate Q bar. Now this circuit with that feedback loop using NOR gates is called an SR-Latch. We'll see where S and R come from in a minute. First, let's take a look at how this circuit works. I'm going to add the NOR truth table up in the corner for reference. 2 things to notice about this truth table. First, A NOR false is not A. Second, A NOR true is always false. Keep that in mind to help better understand how this circuit works. For example, if we put zeros on both R and S, then the first rule, where A NOR false is the same as not A, tells us that the NOR gates will effectively behave like NOT gates, giving us the feedback loop we just examined. So if we magically set Q to 1, then we have that stable feedback loop and the circuit will remain in state 1. Similarly, if we magically set Q to 0, we also have a stable circuit that will remain in state 0. Now let's see what happens if we set S to 1 while keeping R at 0. Because A NOR true is always false, then the output of the bottom NOR gate will be 0 regardless of the current state of the circuit. The upper NOR gate now has 2 zeros as input, resulting in an output of 1. At this point, the circuit is stable and will hold that 1 state until it gets a combination of inputs that'll change that. Notice, however, for reasons we just saw, that if the next change is just to put S back down to 0, it'll stay in that 1 state. This gives us a means of setting the circuit and holding on to that value. Now, in a similar manner, if we set R to 1, leaving S at 0, then the output of the top NOR gate will become 0. That change will cause the output of the bottom NOR gate to become 1, leaving the circuit in that 0 state until something changes it. Because this circuit stores data, a truth table isn't sufficient to describe its behavior. Instead, we use something called a characteristic table. That may sound fancy, but it's just a truth table where some of the columns represent the circuit's inputs and other columns represent the circuit's state. As we just saw a minute ago, when R and S are both 0, the NOR gates behave like NOT gates, and so the circuit just maintains its current state. In other words, Q doesn't change. When R is 0 and S is 1, the 1 forces the output of the lower gate to 0, regardless of the circuit's current state. This results in the upper NOR gate's inputs both being 0, therefore the state of the circuit becomes 1. For analogous reasons, putting 0 on S and 1 on R always results in the circuit transitioning to state 0. The last 2 rows of the truth tables are a bit subtle. Instead of giving you the answer right now, try to figure it out on your own, and we'll revisit this issue during a lab session. So now, based on the circuit's behavior, can you guess what R and S stand for? Which of course tells us why it's called an SR-latch. As you may have guessed, S stands for set. When we put a 1 on S, we're telling the circuit to set its state to 1. And R stands for reset. A 1 on R tells the circuit to reset itself to 0. If neither R nor S are 1, meaning they're both 0, the circuit neither sets nor resets, it just holds its current value. From this perspective, we can see why setting R and S to 1 at the same time might be interesting. We're, in some sense, giving a contradictory instruction by telling the circuit to both set and reset itself at the same time. That, of course, is nonsense, so we avoid using this combination of inputs. Which might make you wonder, how did we end up with an input we shouldn't be using? Well, this circuit has 3 operations: set, reset, and hold. To choose among 3 things, we need 2 bits. That's our S and our R. But 2 bits allows for 4 operations, meaning we have 1 left over. That's the 1-1 input we avoid using. If we want to avoid having an unusable input, we have 2 choices. Either we need to define a sensible behavior for that 4th input. For example, we could decide that when R and S are both 1, the circuit should flip its state from 0 to 1 or vice versa. And in fact, we'll encounter this similar idea in a future video. The other approach is to pick only 2 of the operations, so we only need 1 bit of input. If we were to do this, which 2 of the 3 operations would you keep? Well, a common approach is to keep only set and reset. This choice will make sense when we talk about clocks. Such a latch with a single input that can only set and reset is called a D-Latch. And if I remember correctly, D stands for data. You can build one by simply adding a few gates in front of an SR-latch. Pause the video and see if you can figure out what gates go here to turn the SR-latch into a D-latch. Turns out all we need to do is put a NOT gate in front of the R input. That way, when D is 1, R is 0 and S is 1, which sets the inner SR-latch. And when D is 0, R is 1 and S is 0, which resets the latch. Again, in this picture, there's no concept of hold, but we'll fix that when we discuss clocks in the next video. Okay, so based on this video, you should be able to sketch an SR-latch and a D-latch. You should also be able to explain the operation of these latches. For example, you should be able to trace the behavior of each gate in an SR-latch in response to an input change. You should also be able to figure out the behavior of an SR-like latch made from different gates. So for example, if I replace those NOR gates with AND gates, what would happen? Keep in mind that as you do this, not all combination of gates will produce a sensible circuit. But you should still be able to work through that and determine that the output doesn't work. For example, it might be unstable. In the next video, we'll begin using these latches to build sequential circuits, and we'll also see why CPUs use clocks.